Okay, folks, I hope everybody's doing well. We are going to hop into Module 3 on Engine Support Systems, Resource, and File System. Should be a good one. So let's go ahead and jump into the slides. Don't forget to do your in-class activity and to check out some of the readings for this lecture. Okay, so just a little warm-up to get us started here. And it's actually about a different topic, but related loosely to what we're going to be talking about and something that you're going to be doing, this idea of video game localization. That is the process of translating a game's original language to another, as it says, just like you would with a movie to translate in another language. And the question here is a little bit rhetorical, but just asking if this is a big engineering effort. It can be sometimes, especially if you have voice and stuff. But if you're just working with text, it can often be a quick way to reach different audiences. So again, just thinking about how you might support some of this in an engine is important. If you can see the revenue, and this is quite old by now, this figure. Video games actually, I wouldn't be surprised if it was double or triple this even now. So just something to keep in mind, and something that we're going to think about again at an engine level, at least a simple way to do this. So last time we talked about C++ in a day, primarily focusing on modern C++, a little bit of object-oriented programming, and just this idea that we think about in C++ compile time versus runtime. Again, we have these functions that can actually compute results during the compile time with like static assert or constexpr, and so on, or we had static cast and a few other functions. So just something that might be new, again, if you're coming from sort of a Java or Python world, or even C, but that we can compute results at compile time with C++, which is pretty cool. We also think about using classes to organize our code and the types, but being a little bit careful with our tools, whether we're using composition or inheritance. C++ allows you to get in a little bit of trouble because it has lots of features like multiple inheritance. We talked about that diamond inheritance pattern. We had to be a little bit careful with. C++ also has smart pointers, just like regular raw pointers that you work with in C, but we have smart ones that allow us to sort of avoid some of the pitfalls of C programming. Okay, so you're welcome to use smart pointers in this course. Then we got a little introduction to SDL, just some of the basics, and then talked about the main game loop, and then you guys worked on frame capping in your lab. And then, of course, taking this frame capping one more step further with the Pong game. Okay, so we are, of course, recording here. And just some logistics. Assignment 1 has been pushed to your repositories. So if you check, there's a due date on that, February 22nd. Today is the 7th, so you've got about 2 full weeks to work on that. Let me go ahead and bring up that assignment for you from the right repository. And you're going to be working on the breakout game. So most of it's in the README. This is the game that you'll be building. So check it out, play the game just to get used to it, understand what you're doing. This will be completed individually, and you'll be building your game in this game directory. And some of the things to keep in mind is I'm going to ask you to build a one-page sort of HTML website here where you'll link to the game, the video, and some images. And then you'll have a little Python 3 build, just like we've been doing in our previous assignments. Okay, so 3 parts to this one. I think you'll enjoy it. And again, sort of building on maybe some of the infrastructure that you created in Pong, so you're free to start using some of that code that you're building in the labs. Again, we're trying to build some bigger projects here, okay? So that is the logistics for now, and by the time you watch this or we have our live session, you will also have the next lab available. Okay, so today we're going to talk about engine support systems. Again, this is sort of a big topic here. You can see it sort of falls in the core systems in our diagram. I'll make this bigger in a moment. But it's going to help us provide some structure to our game. In other words, this is sort of the piping or just the infrastructure that's going to hold up our engine to do maybe some of the more interesting tasks. But we're going to do a lot of the more necessary sort of systems-y types of things. So again, I have just listed here as far as engine support systems. What that means is, think about data structures, memory, configuration files, any backbone or foundational structure in our game engine. And I'll briefly talk about or touch on the STL just so you know what that is. as well. Okay. So here's our core systems. Again, just these sort of bigger pictures and things that we'll want to think about. So I'll pick out a few of these to talk about. So we're also going to talk about today resources in the file system. Just thinking about our game assets a little bit. You'll eventually have a lab on this, but also to get some folks maybe with less gaming experience with the gaming terminology down as well as we think about some of these assets. Okay. So the resource manager again plays a big part in loading the 3D graphics or 2D fonts for different things, different parameters for physics things, levels in our game and so on. So I want to talk a little bit about this and how to load resources efficiently. Again, this will be important for your breakout project for assignment 1. Okay, so again, what is a support system? Go ahead and take a moment to pause and think about this. If you've taken a moment to pause the video and think about this, I might have given it away a little bit earlier, but it's something that supports our game engine do some sort of crucial task. And these can be as foundational as just initialization and shutdown of your engine or certain systems in your engine. Managing the memory, what your data structures are, how you're going to hold your data, update your resources, and so on. And you get the idea here. The different configuration files that are loaded, string data. Actually, a really interesting topic because different languages might have different bytes per character and things that you have to support. So, we want to have some good support systems to build a game that we can deliver to or engine rather that we can develop games on for a wide audience. Okay. And these are important to just sort of call out because, it's easy to just think about this class as, we're going to build something really beautiful, which, hopefully we will. But, we often just think about like the rendering engine or audio. But a lot of these other systems are really interesting and have sort of interesting challenges associated with them and are really where, you sort of, for lack of a better term, make or break the engine or make the big bucks by having good foundations to build your engine on. Okay. So this is from our author, Jason Gregory. Again, he says, every game engine requires some low-level support systems that manage mundane but crucial tasks, such as starting up and shutting down the engine, configuring engine and game features, managing the engine's memory usage, handling access to file systems, providing access to the wide range of heterogeneous asset types used by the game, things like meshes, textures, animation, etc., and providing debugging tools for use by the game development team. And then, of course, I don't think any of these topics are mundane. Again, all these topics, these are things you're going to work on in any type of software at some level. You'll touch on some of these topics. So, again, I'm assuming most folks are coming into this looking at maybe a gaming career or graphics or something related to multimedia. But wherever you go, these systems are going to exist and be critical, at some level. Okay, so let's talk about one of the first core systems, initialization and shutdown. Okay, so just a maybe C++ question here, but when I say initialization or shutdown, what do you think I mean? Go ahead and pause the video and think about this. And if you've taken a moment to pause the video and think about this, well, I mean, classes, think about our constructors or destructors. That's when we build new objects, okay? When we create a new object and then destroy an object, okay? Or maybe you think about this more foundationally, it's just like the main function. When we start the program, then it's running, and then eventually we shut it down, okay? But you might also have answered this as maybe like thinking about memory. When you allocate a piece of memory, that's sort of initializing it, filling it with data, and then you delete it or free it. And that's sort of, shutting down part of some data structure or whatever. Okay, so, so here's how we write our classes in C++. Here's another example. And again, please, folks who are new to C++, make sure you're practicing this and maybe even typing in some of these examples on the slides. But something I want to let you know about C++ is, we don't have control when a constructor or destructor is called. So I have this main function here. And I know our program starts here at line 25. It's the entry point. And when we leave scope, the destructors get called, but we can't really choose the order here. So what I mean is, I've initialized these classes here, my system 1, my system 2, 3, 4, whatever these systems are that I've labeled here. But when I terminate the program, it appears to work in a last in, first out order. Okay, so let's see. So I have graphic system initialized, and then, let's see when the destructor calls. So was this one created first? Graphic system, the constructor is called. And then, the collision system, just like a stack, is called in this order. Okay, but what if I have sort of several of these systems and I really need control over which order these systems sort of are initialized? Or maybe, think of it this way, you have a system like networking where your Wi-Fi goes down and you need to initialize that system or restart it or so, okay? So we have to think about that also when we have sort of an unintended event happens that shuts down one of these subsystems, okay? So again, why do we care about this problem? Well, we want the utmost control, right? We're working at the engine level. And it's possible if some of our systems are, sort of connected together, we want other systems to trigger. So here's an example again. Perhaps we want our networking subsystem not to shut down if it is still logging saved data. Okay, so there's maybe some logger here that's logging every little piece of data about our engine possible. But our network, closes or whatever, but we still want it to be running, right? We don't want to say, hey, the destructor just happens to get called because the program, crashed. Okay. And then there might be optimization opportunities as well. We could initialize two systems safely, concurrently, right? When a player of a game, wants to start the game up, we want it to load as fast as possible. So can we do things concurrently? Okay. And again, you might not want to shut down the whole game. Okay. If you change a setting in the game, like the resolution or the quality, you might not necessarily want the whole entire application to have to shut down, right? If you're only changing something that has to do with the visuals of the game, okay? So the solutions that we have is to follow this little pattern here and, take the simple approach here. So we don't really do any work in the constructor or destructor, but rather we have functions called startup and shutdown, or initialize or destroy. Those are common names for them. So this way, we do all of our work in these functions, startup and shutdown. Okay, now I have control over, when is the memory manager starting up, when is it shutting down, I could restart it, and I have just a little bit more flexibility here, okay? Even the order that I'm, destroying things here. Okay, so a lot of gaming patterns, you're going to notice this. In fact, you'll even notice it in our SDL library, which is, it's a C-based library, so not quite C++, but there is like initialize and a quit functions here, okay? It's sort of necessary by the C API, but again, it gives us these functions that just give us control, okay? And some engines go as far as, these systems need to run in certain orders. You could use some, priority queue data structure, for example, if you don't want to have to manually figure out what the order is. So start up and then you give it a priority, right? So if you have limited resources, you could sort of start to do more interesting things here again, okay? So I really like this approach. And again, it seems to work very well if there's no inheritance, right? Meaning these systems can't really depend on each other. Like memory manager and file system can't really be inherited from one another. Otherwise, when that happens, the reason you can't really rely on inheritance is because, well, when you have inheritance, you're calling the base constructor, which you don't have control over from your derived class. Okay, so again, we're trying not to have a lot of inheritance in our systems. Another reason not to like to have a lot of inheritance in our games. Okay, and then as I mentioned, if a system fails, you can try to reset the system and restart it without crashing the game or sort of saving it. It makes your system a little bit more resilient, right? When one of these systems shuts down, right? If you're working in a much more, say, secure environment or an environment where you need high reliability, like maybe an aircraft simulator or something, you don't want to shut down the whole system. You want to be able to quickly start up, shut down, reset, etc., and have these sort of functions where you're doing the work instead of relying on the programming languages requirements about when an object is constructed or destructed. Okay. So again, this pattern works well, but as soon as you have inheritance, that throws the pattern out of the door, because inheritance, again, you lose control over when objects are constructed or destructed, right? That's handled by the compiler, and can often or can be compiler dependent, depending on the language. Okay, so how do we structure our systems to do this? Again, it's going to depend on our engine, but Ogre 3D, which is a free and open source engine, is something we'll probably take a few looks at throughout this course. I'll show an example of it in a moment, but the documentation is actually pretty good on this engine. And I would encourage you to take looks at Ogre as we learn topics. I'll probably have them in the slides for the most part, so you don't have to search too much, but it is worth looking at Ogre 3D and seeing their documentation. So for example, they have a root class. So if you read the remarks about the root class, it says it represents a starting point for the client application. From here, the application can gain access to the fundamentals of the system, namely the rendering systems, configurations, logging, and other systems, okay? So if you look at this, again, in Ogre, you can click this link to see the documentation. You can just sort of observe what's going on in, the Ogre root class, so something that's very important. And it mentions that it is a singleton class, okay? So they have some template to do this. And then you can see all the different managers here for their engine support systems, okay? Which is exactly what we're talking about today. You see the logger, something to do with scene management, meshes, handle particles, and so on, okay? And then when you use the actual Ogre engine, you create a root here from that object, and then you initialize it, okay? And then every system that you have, whether it's the rendering window that comes from the root, or the scene that comes from the root, or a camera that comes from your scene here, but they're all derived from this same root, okay, which controls all of these different systems. Okay, so here's just a quick look at Ogre 3D. Again, the Jason Gregory Game Engine Architecture book pulls a lot of examples from them, so you can just sort of take a peek at it. It's a really powerful engine, and it's primarily for graphics. It really is just a graphics engine, but it's got some other things built into it, so you can do some cool stuff. So I'd encourage you to take a look at this. And in past iterations of this course, we've downloaded it and played with it a little bit, so we might do that, but we will be looking at the code. Okay, so module startup and shutdown, one of the core systems. Okay, so again, in this class, it's fine to not do any work in your constructors or destructors, but rather have startup and shutdown functions that you call. Again, be careful, again, as long as you don't have any inheritance, you can use this pattern. And this is generally a good thing, considered a good thing. Okay, so let's talk about one of the next core systems, memory allocation. Okay, this is a really important one because it gets into performance, something I deeply, deeply care about. But this idea of, we want our games to run fast and to make them run as fast as possible. There's a really cool benchmark that's used primarily for GPUs and CPUs called 3D Mark, that shows sort of the top, very highly detailed environments, and it sort of benchmarks your system. So you can check this out. I believe they've had free versions in the past, or you can get the older versions free if you actually want to run on your system here. But the idea is, to create these really visually realistic and, and games and environments that are simulating physics and artificial intelligence, you have to care about performance a little bit. And memory is such a big part of that. Okay, so memory management, again, this might be a little review of systems for some folks, is a process of controlling our finite CPU memory. Okay, so how much memory we have available in our CPU or different parts in our memory hierarchy. Okay, and typically, we think about this in terms of heap memory and stack memory. And then, of course, there's stack memory as well. So heap, again, is memory that's allocated during runtime when you do new. And then stack memory are your local variables. Okay, local and variables, variables that are passed into functions that are copies and so on. Okay, and each of these has different trade-offs. So the heap, is for long-lived objects that are probably going to persist for a long time in your game or environment, or tend to, and maybe that's why you need control. Or again, they're just created at runtime. And stack memory is short-lived and often reclaimed memory. Okay, so you put something on the stack, some temporary value, and then you pop it off the stack when you're done with it. Okay, so most of the time when you're making function calls, you're making lots of copies on the stack very, very quickly, and then reclaiming that memory. Okay, so again, in C++, we manage our memory with new and delete, or delete with the brackets for arrays. Again, just make sure you do that. We have a memory manager already sort of built for us in C++. That is, when you use the new and delete functions, this is your allocator, we would call, that manages how you grab memory from the operating system using new, and how you reclaim memory from the operating system using delete. These functions here. Okay. So again, new in C++, this is what we're going to be using. Folks who have taken system, maybe you've gotten used to malloc for the memory allocation. And we don't want to mix these because these are two different allocators. The C++ allocator is new, the C allocator is malloc here, okay? If you mix them up, you'll get really weird results in your program. If you try to free something that you've newed, it probably is going to, again, cause strange results. Okay, so again, when we're dynamically managing our memory, we're extending our heap, okay? That heap section of memory that was back here. We're making this section bigger because we're growing it at runtime. Okay, and this is very slow. Can anyone remember why this is very slow to allocate on the heap? Go ahead and pause the video for a moment and think about it. And if you've paused the video and thought about it for a little bit, the first reason is that the allocator, the new function, is designed to handle and book and keep allocations of any size. New is what we call a general purpose memory allocator. That means it's going to do pretty well for most applications. So if you're allocating 1 byte at runtime, or 1,000,000, or 727, or just whatever the random increments are, it does a pretty good job at all of those tasks. So it's not very specialized, but it's just a general purpose allocator. Okay, so that means it has to handle, or it's designed to handle, a bunch of different scenarios of small allocations or large allocations. There's certain optimizations you can do if you know exactly how much memory you're going to allocate. But with new, we don't have many constraints. It just needs to be handled anything, right? Whenever you new something, you expect it to give you memory. The allocator will do that work behind the scenes. What I've got here on the right side is just a portion of the new function in GCC here. So you can see what it looks like here behind the scenes. And there's lots and lots of different versions of it that have to be written, and there's lots and lots of code. It's several hundred lines of code for the main body of this function here, okay? But the second reason allocation's slow is, context switch has to take place, okay? So again, review of systems, I suppose, you're running your program, it's running in user code, and then the kernel, or whatever operating system you're running on, whether it's a PlayStation or a PC or whatever, your application's running, and then you make a system call every time you allocate memory. So that causes a context switch, so your game's running. Some particle effect is created, because there was an explosion. So you have to create these particles. You don't know how many because you have to generate them at runtime. And then you sort of pause the game for a moment. The operating system has to take over, allocate the memory, and then you can resume. Okay, so again, it's sort of like what we're doing with the It's almost like adding an SDL delay in your game, simulating this effect of having to literally pause your game, move over to operating system. Maybe other tasks get scheduled to execute as well, and then it returns to your game. So that can result in lag in your game, okay? When these effects, this very exciting event of this explosion here is happening, you don't want your game to lag and freeze. That takes you out of the moment, okay? And that can happen if you sort of poorly do and memory allocation, right? It takes many cycles of your CPU. Okay. So the order again, how much is this slowing things down? I haven't measured personally. Maybe I should find a way to do good measurement. I mean, we could simulate this. But context switches take on the order of hundreds to thousands of cycles. Just to do that switch, where it's just executing a regular instruction, especially if it's a simple instruction, it's like 1 to 100, even for the most complex one. So you're already, roughly 10 times slower, in the sort of average case, every time you have to do that. And here's a little timer function if you want to measure cycles. I actually do have some code to do this if folks are interested in measuring some of these things. So you could call the new function and just measure how many cycles it takes using RDTSC. It returns the cycle count, an approximation of it. Okay, so the ideal memory management, or how you really want to build your game engine and the games around it, is just to allocate once, because I've told you this thing takes a big long time. Every time you call malloc or free, so ahead of time I've already allocated memory for this explosion. I don't have to use it, but the memory's already been reserved for it. Okay, so if I pre-allocate memory, then I just have this giant chunk of memory already reserved for my process. I don't have to search for it. I don't have to figure out if it's available. It's just already available. And then we can write our own custom memory allocator when a programmer asks for memory, okay, from this big chunk of memory. So this is the ideal solution. This is ideally what we want to be doing. Okay, so if we want to write a custom memory allocator, we can override the function of new and delete. And again, maybe I'm giving away why we want to do this, but go ahead and pause and think about, why we want to write our own custom memory allocator. Okay, and then if you thought about this a little bit, again, it's for performance, so that's sort of given away. So if you said performance, that's exactly why. That's why we're doing all this work. But we can also figure out, our memory access patterns, exactly how much memory we'll need, so that we can do this pre-allocation for our game. Okay. And memory access patterns really, really matter in game programming, right? Figuring out how our memory is accessed and what portions and what subsystems is memory being used. And the goal is overall to reduce fragmentation and improve caching. Okay, so let me get to this on the next few slides here. Okay, so the idea is over time when you're running any program, memory is going to become fragmented or non-contiguous. Right, so you start off your program, you freshly load up your operating system, whatever operating system it is. Maybe it's a PlayStation, maybe it's a PC, but you have a bunch of free memory. And then you allocate some memory when you start a program, and you have less free memory. Then maybe within that program, you do some more allocations. You have less and less and less. But, you're working through that program or game, and, you beat a level, so you deallocate some memory here. You delete it, right? So you have all these little chunks here, or fragments, okay? Then after, if you continue this process, eventually you just have these after several allocations and deallocations or deleting the memory, you just have all these gaps here, and we call that fragmentation, okay? Then, we want to know at the least if we have enough free space to do some of these allocations, okay, in our allocator. And if I need to, allocate some really big asset here, like this art asset here is pretty cool, but do I have enough memory to do that? And if this is only available free chunk here, probably not. Okay, so sort of we're in trouble then. Okay, we've sort of poorly managed our memory, or what I'm getting at here is we've let the sort of general purpose allocator sort of just handle this, deleting memory when it's done, but not really recombining it or maybe moving memory around to give us more efficient and bigger blocks, right? Because we have all this fragmentation. Okay. So what we want to do or need to be able to do in our allocators, and the new allocator, etc., does some of this, but be able to sort of fill in some of these holes or move around and sort of shift pieces again. So I can have this big chunk of free memory here when I need to load a new asset. And sometimes it's not even loading a big asset like this 3D model here, but it could be like pre-allocating the next level in this chunk. So again, you need lots of available space often in big chunks. Okay, so this rearrangement needs to sort of be happening in the behind the scenes here. Okay, so usually you're doing some pointers, magic in a sense to sort of move some blocks around to figure out where these blocks start from and where they end, and kind of move the data a little bit. Okay. If you want to see a visual of this actually happening, you can use a tool like a disk defragmenter in Windows. I think it's got a little visualization where it might show you how fragmented your memory is, and then sort of clean things up. It's just a generally good thing to know about. Okay. So again, there's different memory allocator strategies I just want you to know about that games use. So again, it's enough that we have new and delete for now to use, but when you have a game, you might have several different allocators that just utilize that big chunk of memory for specific tasks. Okay, so here's 4 types here I want to give to you. Okay, and I just want you to, for now, your takeaway is just to start visualizing memory. When you allocate it as sort of these chunks that you have. Understand that it's not an infinite resource, and it really is a challenging and sort of fun problem to tackle, because this is where you can really push the limits of games. In fact, this is why PlayStation 5, for instance, the games look so good, because they've done a lot with the memory allocation. Okay, so let's talk about some of these strategies though first. So stack and pool allocators. So stack allocators themselves don't have any fragmentation problems, okay? Because you just have a stack here. So here's a stack, and you allocate on the top. It's just exactly a stack data structure, and then you have to remove the blocks in the order of a last in, first out order. Okay, so maybe long-lived items and stuff get allocated first, and then as new things happen, they get allocated. Okay, so this might make sense if you sort of use this stack-based allocator, because then you're guaranteed to have the largest amount of free space always available, because there's 0 fragmentation. Okay, another strategy you can use though, and I'll actually just divide this up into a slide just to make it easier. So that'll be coming up, but this idea of a pool allocator. And these don't really degrade from fragmentation, but they still do have a fragmentation problem. So what a pool allocator is you just say, hey, I need several or fixed size of memory here. Let's say it's a terabyte, something really big here. This is a terabyte, but I'm just going to divide that into 20 or so equal chunks, and they're each going to be the same size. Okay, so you have a bunch of blocks that are already sort of pre-allocated. Then the allocation can become a little bit more predictable. And this is a useful strategy if you know exactly, what your biggest block is going to be, okay, or what the sort of size of each of these blocks are going to be, okay. So that's the idea. So you have a pool of memory that's already been pre-allocated, and then you can just grab one of those blocks or pointer to one of these blocks when you need to allocate some memory, okay. Now you can take each of these ideas a little bit further too, by having different strategies. So this is a stack allocator that you can have as well, but it's a double-ended stack allocator. Okay, so you have the sort of top portion of your stack for temporary objects, maybe explosions or whatever. So maybe this top part of your stack, and the bottom portion is used for sort of larger assets. Okay, this lower portion, things that are going to live a long time, the main character, the level. You can sort of grow from there. And that way you still, again, have this maximal amount of free memory here with 0 fragmentation. Okay, so it's a little bit of a different take on a stack structure. You're almost accessing from the middle of it right? But if you just have pointers, you can do that. So just a new idea for you to think about, a double-ended stack allocator. Okay, again, here's the idea from a pool allocator. So you just have a bunch of fixed size blocks and then a linked list type data structure that points to a free block or the first free block that's available. Okay, folks who have taken systems with me, either the grad version or the full semester version, we build a sort of pool allocator or a variant of it. Okay. Okay, some other ideas that you might run into for memory allocation is this idea of a single frame allocator. Okay, you just allocate some fixed size memory, some block of memory at the start of every frame. Okay, and then this memory will also be freed every frame as well. Okay, so anything that needs to persist beyond a frame can't use this memory. Okay, so it's just sort of like a temporary memory. I'm going to fast forward us here to the double buffered allocator because this is similar to what something that we've seen before. Okay, so double buffered means you just allocate some fixed size of memory, but you do it twice. Okay, it's going to persist for at least 2 frames in your game. And think about this. Have you guys seen this sort of double buffered allocator before? I'll give you a moment to think about it. And if you've paused and taken a moment to think about this, you actually have in computer graphics for those who have taken it, or in SDL, it's actually using the same strategy. So you will, as you read through the documentation. But what you're doing is you have a fixed size, however big your window is. Mine here is, I guess you can't see it, but it's roughly a 4K display. So however many pixels fit in this image here, we allocate twice as many or twice as much memory, 1 for the first image, and then we draw to that sort of front buffer here that you see where my red laser pointer's moving around. And then the next frame, you display onto the screen that image. Then you start drawing what the next frame is going to be. Okay, so that's the idea of a double buffered allocator. Okay, sometimes we just call this double buffering, but again, it's the idea that every frame that you draw, you've just pre-allocated enough memory to draw an image on. Okay. Okay, so again, where I'm getting at with all this memory allocator stuff is best practice in games and that we want to support in our engines is just to be able to allocate one giant block at the start. Okay, there's some ideas on how we can sort of control our memory and write some custom versions if you want in this this write-up here, which is kind of cool. That's where this figure comes from. But there's a lot of power in this idea, again, because, again, if we allocate all of our memory at the start of our program, and then we get that memory into some data structure, we can do some pretty cool stuff, like tagging the memory for which system it belongs into, or when that memory was allocated. Because if we know when it was allocated, maybe we can take advantage of that to figure out the memory access pattern, or use something like this double-ended stack allocator to sort of put our long-lived memory in one side of the stack, and get some benefits from that. Okay, and overall, again, what we're getting though is going back to this other point of, because we've already done our one big allocation when we start the program, we avoid any context switch. If we own the memory, it already belongs to our process. We don't have to go to the operating system for any more. Okay, so we get great performance by doing that. Okay, so again, memory and performance, fragmentation, it gets as bad as however big our biggest object is, I guess, that we can allocate. So that's something to keep in mind. But the other question is, how fast can we access our memory for performance? Okay. These next slides, I think most people have probably seen in a systems class. So I'm going to run through them relatively quick. But again, the idea is, okay, we've allocated all this memory ahead of time for our process. So really quick, this diagram, the idea is we have hard drive memory, which we have a lot of, but it's very slow memory. And then we have things like flash memory, which we have a little bit more of, but it's slow. We have our DRAM, which is the just random access memory that's relatively fast, and we have a decent amount, right? Most of your machines probably have 8 gigs or 16 gigs. And we have our caches, which we have a lot of, but not much capacity, because it's expensive and various reasons. Then we have our processor with roughly 16 general purpose registers and a few other registers that are very, very fast, but are very expensive, and we have very few of them. So again, we want to be working with our memory towards the top of this chart here, because it runs a lot faster. It's a lot cheaper to do the different memory accesses. Okay, so we're about 40 minutes in at this point if you're watching on 1x speed. So, give yourself a stretch break if you need to. We'll have several breaks. But then I want to just kind of cruise through this next topic as a reminder for folks. So give yourself a break. If you're just joining back with us or powering through the lecture, what I want to talk about is caching, which is really, if we look in this diagram here, again, recall the processor cache. We don't have a lot of this memory, but it is very fast. We certainly have more of it than registers. We have a few kilobytes or maybe megabytes of cache memory. So if we can keep our data up here towards the top, then we sort of win performance-wise. Okay, and our clients get a better sort of deliverable. Okay, so just really quick, what is a cache? I'm going to fly through these because you've likely seen these in systems. People in my systems, of course, have seen something similar to this. But again, cache is a small, faster storage device for memory. It's sort of a staging area for pieces of your data. Again, it's an abstraction to speed up your programs by putting frequently accessed memory into a location where it can be quickly accessed. Okay, so we want the data to be in our cache. Otherwise, we get what's called a cache miss, where it has to traverse down this memory hierarchy to find the appropriate copy of your data, and then move that data temporarily into the cache and so on. So that's sort of expensive. Okay, so remember, we have these terms cache hits and misses. We want more hits than misses. That means we're doing a good job of finding data that's frequently accessed. Okay, and then again, just the general concept of a cache again. So here's our main memory, maybe our DRAM or a hard drive. We just have lots more data here. So here's the different blocks of data. In our cache, we have fewer of these blocks and a few values that we've recently accessed. So this 8 is a copy of this value, this 9 is a copy, this 14, these are all copies, this 3 is a copy of the data. Okay. And if in our game we're requesting, block 8, I search in my cache first. And it's faster to look through 4 things than to look through, all of your memory to find that data. Okay, so it is in there. We can leave it in there, and that's good. But if we try to look for 0, so I have to search through all my cache, so that costs me something. We find out that it's not there. So then we have to search in the next level of our hierarchy, and we find that 0 is now here. So then we have to move it into the cache, figure out the right place to move things in the cache, evict something, and then update that value all in our memory hierarchy. So that has a cost to it. Okay. So again, this is an expensive process, especially when we get a cache miss because we have to move something into the cache, which takes some time, and so on. Okay. If you want a good review of the caching, just watch this video from about the 7:40 to 10:40 mark. Just click on the link here. I'm going to open it up. John Lycos, I've seen him give this talk live, actually, a few different iterations of it, and he'll review the importance of caches to you. Okay, again, most folks who have taken a systems class, this is maybe a review for you, but anyway. So the takeaway is a cache line from this video brings in data that's nearby. So we have good spatial locality. And then, it's likely that we're going to access memory that's close to proximity, other memory that we're accessing. Okay, it's the principle of locality, where you tend to access things over and over and over again in time. This is temporal locality, right? It's a single value in a loop you're accessing over and over and over again. So we want that data to be in the cache. And then spatial locality, and that's when we access some piece of data, we're likely to access the next item. Okay, so if you think about any time you've ever iterated through an array, you usually, access that first value and then the next value and then the next value after, then the next value after. Okay, so if you bring in one value, you might as well bring in a cache line or a series of values, some fixed amount next to it. Okay, so in order to exploit locality in our code, we often try to organize our data into contiguous blocks versus non-contiguous. Okay, so question for you folks is, which do you think will be faster? Which data structure, a linked list or an array? Okay, I'll let you pause and think about that for a moment. Okay, so if you've paused and thought about it for a moment, we will continue, but very likely it is the array, okay? Because the data probably gets better, at least spatial locality, and probably, it's easier on the cache to just load up an entire cache line for that array, okay? So things like a vector data structure in C++ are often very efficient. Okay, so just a few tips on data locality. It can be very easy and hard to find places for optimization. Again, this is why we will need eventually a custom allocator to tell us how we're accessing our memory, how good of a job we're doing, etc. Okay, even functions, are nice in the sense that they have all of their code contiguous, except when they're being inlined. Okay, so I need to talk about that for a moment. Functions themselves are laid out in memory by the compiler in the order they appear. Okay, in a C++ file. Okay, let me just load up some code here because this might be getting a little bit too abstract. But this idea that in memory, so let me just open up how about lab 1 where we have some source code. The compiler, when it generates this code, let me go somewhere where there's functions, it just puts the init function and then the update function after it, and then the render function after it, and then this, constructor after it, and so on. Okay, so even the functions are laid out in a contiguous order. So we can think about our sort of caching from our instruction cache. What functions are we going to call what instructions in the order that those appear. Okay, so that's another way to get sort of performance. Okay, and any code that we're executing, it's going to be executing a lot. Generally should be kept in a sort of small and a tight loop. Okay, not lots of big blocks and so on. Okay, other ways to sort of improve performance by avoiding lots of copies on the stack is to use inline functions as well. Think about our memory. Okay, what's an inline function, you might ask? Inline functions are essentially copying and pasting the body of a function. So here's function 1, and I'm copying and pasting it into main whenever I inline it. That's just take the function body and insert the code here. Okay. What that does for performance is it reduces the overhead of making a function call. So anytime you make a function call, you have to make a copy, or often have to make a copy of the arguments, as well as a copy of the return address, and all those values get pushed onto the stack. So then you would have some stack allocations, and we know that memory is sort of valuable, so we can avoid that. And then you also improve the data locality in the sense that the data is prefetched here. So when you're executing your instructions one after the other, your CPU is usually looking a few instructions ahead, and it can see what's going on here without having to jump into another function here. Make a long sort of jump over to that other function. And sometimes that long jump actually means physically in memory, a long jump to figure out where this piece of memory is and start executing those instructions. Okay, and that happens a lot in library code, for instance. Okay, so that's just some sort of summarizing the advantages and disadvantages of an inline function. Okay, just some numbers that might be useful just to put some numbers to this. If you want to see, looking at the memory hierarchy, how much faster is the cache as opposed to the disk, for instance, the cache cache access is 0.5 nanoseconds, so very, very fast. I don't have a good analogy for how fast that is. But versus reading something from your hard drive, so when you're loading something for the first time, which is 10 million nanoseconds, right? Or 10 milliseconds. This is about as fast as you can blink. This is about 20 million times faster than that. So that's how much performance you can get by arranging your data in a reasonable way. You get better performance, better energy utilization, all these sort of things here. Okay. So keep this in perspective again. Game running at 60 frames per second, right? You've got 16.66 milliseconds to work with. Okay. If you do a 1 megabyte read from a disk, that could pause the game for one millisecond here. That might be enough to notice the lag, right? Going at 60 frames per second, you're already using some of this. That's 1/16 of your budget here. Whenever you read from disk or load 1 megabyte, roughly one image. So if you do that inefficiently, you're sort of in trouble. Okay, so and what's 1 second or even 1 millisecond in your game, you're going to be building breakout. That's enough to sort of lose the game, as you'll see here if there's a little bit of lag here. Okay, and we don't want to disappoint our customers. Okay, let's keep moving on and talk about the engine configuration, another sort of core system. So we've talked about shutdown and startup. We've talked about memory allocation a little bit, a little reminder of some systems topics, and let's talk about the engine configuration. Okay. And this is something we often see when we launch a game, maybe from a main menu where you see some sort of graphic setting. And, this is where you're going to try to fine-tune your game, so to speak. Okay, so here's an example for you, just what I mean here. Okay, so often what you have behind the scenes is just some sort of configuration file where you have some sort of key and then a value that you set. Okay. And if you look inside any games that you've downloaded or happen to have some file access to, you'll probably see a .cfg for configuration extension. Sometimes they get fancier with JSON or YAML style formats to format the data, but something like this will be just fine. Okay, so you're going to actually do something in your breakouts project to support 2 languages in your game and have a configuration file. And something like this is just fine to start. Okay, so again, you can sort of get more and more advanced with some of these. And for instance, I think this is a fun one, particularly for our undergraduates or folks who have taken PDP, I think where you use some scheme. Naughty Dog Studios, where our author is from, and which has done most of the big PlayStation titles, things like Last of Us or and so on. But they use Scheme for some of their configuration files. Okay, so you can actually see it in practice and maybe actually get to use it out in the gaming industry someday. So just a quick note on that. Okay, so just a quick note on containers. We won't do anything in class. We're online, but just some container data structures. And knowing your data structures well, or at least by the time you finish this course, will be important. You'll get sort of familiar with them. But I just want to talk about a few, and I don't see them going into super detail like Fundies for folks who are taking the Fundies 1, 2, 3, etc. Series, mostly undergrads. But here's your container types that you get in C++ for free. Okay, you can look at them on c++.com reference. So these are data structures you want to be pretty familiar with, at least just what the differences are, right? We know arrays, vector, that we have here, linked lists, and so on, trees, your binary trees. We want to be familiar with maps and so on. The container operations that you have usually are insert, remove, a way to sequentially access all the data, so how you sort of iterate through them, if you have random access, so meaning like arrays, you can just access anything. A linked list you have to iterate through. And then maybe other operations like find and sort. These are sort of the standard operations in the C++ standard template library, which I just call the STL. Okay. In C++, the preferred way for iterating through a data structure is not to use a loop and then with a sort of for, int I equals 0, well, or less than the size, but it's to instead use a iterator, which basically has a pointer to the start of the data structure, and you'll iterate through with that pointer to the end of the data structure. Okay, so whether that data structure is a tree even, you have iterators available. But this is sort of the preferred C++ style, especially if your intent is to find something or just iterate through the entire collection. Okay. There's other little things in our C++ code. You see this plus plus for the iterator. So this is just sort of an aside. Plus plus versus so pre-increment versus post-increment. Does anyone actually know which one's faster? And I'll pause and let you think about that for a moment. But historically, pre-increment has one less instruction to it. So, whenever you do your adds, if you're just intending to add one, you can favor pre-increment. There's one less assembly instruction there. So you go a little bit faster. And it's actually a memory access, so that's even better. Okay, now game engines will often also reinvent a lot of these data structures for their purpose. Okay, so I'm telling you about the C++ STL, so you know it, and that it exists, and it's fine to use in this class, but it's the standard template library, which means it's sort of, again, general purpose, good for most of the tasks that it does, but it's not always going to be optimal. Right? There might be functionality that you don't need, for instance, in particular data structures that make them sort of heavier. So, there's lots of optimization opportunities in STL. Just a fair warning that, we'll probably build some header-only libraries or small libraries that do a task, faster than something in the STL. But it's fine to just use the STL in this class. Okay. So again, just some data structures to remind you. Linked lists, please be familiar with these. You have a head and a tail and can sort of iterate through the data structure one at a time using pointers. So some common operations here. Here's sort of the generic linked list structure. Some things you might want to be familiar with. Again, in C++, we could spend time talking about this in discussion, but templates is C++'s version of generics. We usually have a struct here when we're defining things like nodes or classes, or rather data types that don't have member functions with them. We usually use struct, but remember, structs and class are almost the same, other than the default access level. There's other data structures with lists, like extrusive lists, if elements can be shared amongst other lists, versus intrusive list. So you might see these two different types of data structures, as if elements are unique to the list. Okay, this is likely what we're more familiar with, or likely our intent when we're creating a list, that it's a list that doesn't know about anything else and has its own sort of elements with it. Okay. You want to be familiar with hash tables. These are dictionaries in Python. Java has them. I think they just call them hash table as well. You can look, I have a lecture on this in C++. If you want to look at sort of a nice basic lecture on it. For hash tables, they're called maps in C++. And strings you'll want to be familiar with. You'll likely be using them a lot. And how are strings implemented? Just a little refresher if you had to guess, or if you remember in C how they're implemented. If you've taken a moment to think about that, it's just an array of characters. Okay, so this is something to consider. Now, again, with part of your homework, you'll have to be a little bit careful. Because we're going to do some localization or adding another language. So depending on the language that you're trying to support, you might actually have to use 2 characters at an index to store a particular value, depending on what language you're using. All right. Okay, so here's a little bit on string processing if you need. Algorithmically, some things to just keep in mind with these data structures are some of their operations. Some of these sort of character by character um, comparisons with strings can be expensive. They can be O(n). Instead, you probably want to hash the string value, and then you can do a sort of integer comparison, or maybe do a bitwise comparison of the characters. So just some things to think about algorithmically. Okay. So the standard template library in C++, again, is the most well-known thing. It's what I'm expecting you to use in this class. Some folks who have taken the C++ class might have also seen Boost. It's another free set of libraries. You're welcome to use that for your projects, however you like. And some of the pros and cons. I would say if you're familiar with Boost and have used Boost, you're welcome to use it in this class. You don't have to learn anything about Boost, but just know it's an alternative sort of C++ library with different data structures, many more data structures and libraries to do interesting things with. Okay, so you might try running. I'm going to give you in the sample a generic linked list that you can run on your compiler and try to play around with it and try to answer some questions on the in-class activity. Okay. So where that is, just to be clear, if you go back here to the main website, the code examples, we're on module 3, and there will be a file here, locality CPP, that you can try running and just run some little experiments with some data structures. So traversing through a linked list versus an array. And then you would go to your, for module 3, in-class activity. I believe I already have set up here where you can talk about, let's see, I believe I asked some questions about locality here. So just if you want some ideas about it. Okay. Okay, so with that said, go ahead and give yourself another break if you need it, and then we can resume shortly. Okay, so hopefully you gave yourself a little bit break and are joining us. And I want to talk about the next sort of topic that has to do with a lot of these, things that we're talking about with our engine support systems, but just creating resources in a game. Okay, so I've talked about some of these systems that are going to support it, and starting to remember some of these ideas about memory and how we allocate data and so on. But we want to think about what resources make up a game, right? And they're essentially the multimedia resources, right? Assets that have been created in some sort of digital content creation tool, Photoshop, Paint, Maya 3D, Blender 3D, etc. These sort of applications, Audacity, Ableton for sound folks. So my equation for a game is you're essentially doing the code that you're writing plus the art is what makes a game. Okay, so let's get familiar with a few of these tools, just so you sort of know. Some sound and music assets are created in tools like, again, Ableton or the Fmod API, just sort of play around with them, usually in .ogg or MP3 formats. MP3 maybe not as much, actually, because it's a compressed format, so the quality might not be as good. But sometimes you want a compressed format because it's faster to load. That's just sort of an aside. But some of these programs like GarageBand, where you're creating these actual assets, or maybe just live recording on a mic some sounds. For image assets, you're usually using a program, again, like Photoshop, GIMP, or Paint, and sort of working with BMP, PNG, EXR, or JPEG formats, okay? And usually in games, you're working with sort of lossless formats, so the image looks as sharp as possible. JPEG is a lossy format, meaning it's compressed so that you lose some of the original texture. .exr is just a special format from Industrial Light and Magic, and they can store sort of higher color ranges in this format, or even floating point values or things like that. So just so you're aware that depending on the industry you work on, these things really matter. Like a Pixar movie, you're not generating PNGs. You're doing something even better than that. That has a higher range than 0 to 256 or whatever for each of the color channels. For video and movie assets, you're probably using some sort of 3D package, maybe. Maybe you're rendering this in Maya, where you actually have the assets, Maya 3D, Blender 3D, 3ds Max, etc. Those types of programs, and then maybe using a tool like Adobe After Effects to sort of work with the scene. Okay, a lot of game engines these days also might have built-in cinematic tools or plugins for sort of doing things, sort of in-game cutscenes. So that's also something to consider. Okay. For your 3D assets, some of these 3D programs that I mentioned, Max, ZBrush, Blender 3D, you're usually working with a 3D format with geometry data. Sometimes that includes animation data, so how the individual vertices move around. And most engines also have their own sort of proprietary format as well for how they want to store their data. And that format's sort of optimized for how it's loaded in the data and what features it supports. Okay. And something we want to sort of consider too, or maybe that you haven't thought about, is the asset toolchain or the asset conditioning pipeline, which is how do you take some of this data from these tools and then format them in a way so that your game engine understands. Sometimes people go as far as building plugins for Maya 3D that can export the data in the exact right format that the game engine understands. That's perfectly normal. Okay, and then it's up to the game engines to load those resources in that format. And often they can do it quicker too, because when they're parsing the actual data, it's data that they know how to support, it's arranged in the right order, etc., etc. So that can be, again, to your advantage. Okay. So again, if you have your own format, you don't really have to worry about this next slide as much, but sometimes exporters don't export data properly. So if I'm working on a 3D project and exporting a 3D model, maybe the scale of the model is different between the two programs, meaning a 3D file in one program is way bigger than the other. The scale's off. Maybe it's working in meters instead of feet, what you're expecting, okay, in your game engine for the unit. So often you have to use what's called a resource compiler to sort of massage the data and do this sort of rearrangement of the data, okay? So there's some sort of examples of this if you want to look at, okay? So my question then is it as simple as just loading in a bunch of resources, right? So we can write our code like this, right? My image 1, 2, 3, etc. SDL, we have a function that'll load and parse BMP files. So we just sort of do this one after the other, right? Let you think about that. And of course, why I'm asking it, there's going to be more to this, but let's look at how load BMP is implemented. And what we really need is a resource manager, right? We need some sort of support system. Okay, so here's going to be our sort of running example. So we have some resource here. That's our image that we're going to label this. And we want to load it up, right? So we just take a file path and load the image, okay? So the resource manager, what it does in our engine is it sits on top of files, right? And these could be images, 3D models, music. We're just working with a BMP image, okay? And we know files in a computer are a collection of bytes just stored in memory, okay? We've talked about memory previously. It's really important for performance, and that's a scarce resource, okay? So the job of the resource manager, or sometimes called the asset manager or media manager, is to load the resource at the proper time and unload the resource at the proper time, okay? So this is, again, talking about, well, where we started at lecture, with thinking about startup and shutdown of our resources. And that's it. That's the two jobs, okay? It's going to sit on top of our file system and load stuff and then unload it. Okay, so if our resource manager sits on top of a file system, then it should wrap the file system functionality. Why is that? Okay, what do I mean by that? Maybe pause and think about it. If you've unpaused and thought about it for a little bit, well, we need to think about cross-platform compatibility. A Windows file system is different than a PlayStation's. And again, it just gives us control over how files are being manipulated. Okay, so let's just dive into this a little bit more. Very, very quick file system review for folks. Again, maybe you see some of this in systems, maybe some or all of it. But you have absolute and relative file paths. Right? So if you specify an absolute file path, that's the full path from the root directory to your file. So this is what you won't want to do in your games, right? If you have home/mic/ bitmap1.bmp, that's going to be different on your system, right? So instead, you want to use a relative file path from your root. It'll be something like dot dot, slash my bitmap1 or whatever. Okay. So that's something to keep in mind here. I think folks probably know about some of the navigation in Unix. And again, just this idea that paths and so on vary depending on a platform. So again, you probably want some abstraction. Pretty much everybody except for Windows. Windows messes this up, but they use a backslash for their locations when you're looking for them. So sometimes you'll see C:\\/ or the /. Pretty much everyone else is backslash when you look at the file paths. So again, I'm just mentioning this because when you work with someone on a different platform or operating system, you might have to, like one of your teammates later, make some of these distinguishments. Just something to keep in mind, maybe something you can handle in the resource manager, right? Which is going to sit on top of your file system and do all the loading of the files for you. Okay. So again, just a high-level view of a file system API. It should let you do very basic things like read in a file path, open and close the file, read the contents of the file, and perhaps asynchronous file operations. So this is the part that might be new that I just want to introduce, okay? That'll be actually useful for us in our game engines. Okay, so again, the file system is responsible for performance in one area of our games, and this is load systems. So, if you can read this article if you want, but games, and this is sort of the problem with games for the longest of times, have always had bad loading times, okay? And we want to do a little bit better. And why? Go ahead and pause and think about this. Why are game loading times so bad? And the answer is, well, our GPUs and CPUs got a lot faster over time. Our GPUs more so, where we do a lot of our work, but our hard drives, this is what your hard drive looks like, they got steadily faster and, not very much. Okay, so if our games have better graphics, with better assets, with higher resolution, that means we're trying to load a lot more from a resource that's very slow, okay, our hard disk. Okay, so loading a model like this, which has lots of different polygons, takes a lot of time. Right? And this is probably 40 to 50 megabytes of data here, just this one model with all the different textures, mostly texture data. Okay, and people don't like loading screens. They don't want to wait a long time. So how do we minimize this? There's two ways that we can work with our file system to sort of minimize this. Okay, we can buffer our data, or really we have two ways to read and write data. Buffer data means we're moving data in blocks, sort of streaming it in, and then unbuffered, which means we as programmers manage the data buffers ourselves. So essentially one just system call per read or write. Okay. And then, there's some other operations we might want to think about, like what the medium is, meaning, hard drives are slow, so could we use something else like a USB drive? To sort of speed up how we load data instead of a hard disk, which I claimed is really slow. Okay, so we need these sort of file operations to load data and to do it as fast as possible in either a buffered or an unbuffered way. Okay. So for Unix users, you could do this little example here. And actually see why printf is much faster using buffered data. Okay, what I'm getting at here is, again, this sort of distinguishment, depending on what file operations you do, is buffered is going to be a lot faster because there's less system calls. You can actually observe this by running a program called strace on whatever program you're executing and see how many write or read calls are actually made. Okay. Okay, so if you only see one write operation, which is here, or rather unbuffered, sorry, apologize, I misspoke. That just is one write of a really big chunk of data, okay? Okay, so the other thing to think about with file systems, and then we're gonna wrap around to actually, loading our data, is to think about, are we accessing in a synchronous way or an asynchronous way our data? So synchronous means that there's some ordering that must be enforced. It's synchronous, right, together. So, with synchrony, as opposed to asynchronous, which means without synchronous. Okay, so here's an example of opening a file with the data not being returned until the file is fully read. So we have a synchronous read file. Takes in the file path, the buffer, how big the buffer is, then how many bytes have been read. So here's your file. You open it up. If it's been successfully opened, you read. You do your read call until all the data has been read here. Okay, and then you finally get down to your next function. Or you return from this function here. Here's where you're doing your synchronous read, and then print success read however many bytes. Okay. Okay, so this is a blocking file operation. This means while your hard disk is reading this data, it can't be doing anything else. It has to finish this task. Okay, so oftentimes what happens is if you're on a Mac, you'll see that little color wheel start spinning around. If you're on Windows, you might get the hourglass. If you're on Unix, your system just freezes if this is a really, really, really big file. Okay. Instead, what we like doing is maybe asynchronous file I/O, or another strategy at least that we could try. And that means that events happen without synchronicity or without order. Okay, so this happens all the time when you click on a YouTube video. Likely this video that you're watching now is you'll see it just starts playing right away, and it buffers a little bit ahead here. Has a buffer with some of the data, and then it's sort of loading data without synchronicity, right? It doesn't have to wait, but it's starting to sort of preload the next piece of data here. Okay, so asynchronous I/O works by handling requests in a different thread. So there's a different thread on your CPU working and bringing in data. Okay, should we worry about this? Why not just use the C library? Those write functions. I said those were pretty good at just reading a big block, but we might want to have some other abstractions like asynchronous I/O. Okay, and then that gives us a little bit of control on how we read our data and whether we need to read it all at once or without any synchronicity. Okay, so here's just a quick asynchronous I/O. Example, you can do it in Boost. There's a library, but I'm just going to show you in regular C++, just to show you async. So here's a main program here. It's got a function here for file loaded, and then I've got a little sleep function here. Okay. So what this is going to do is it's going to start loading the resources even while the process sleeps here. It's going to just start loading the resources right away. There's a little loop here, and then this loop pauses automatically. Okay, so here's my main. The function here is called a future, in that it's going to try to get a result later. Okay, in C++, it's just called a future. The important part, though, is just to know about this async here, this asynchronous call that says, hey, launch this thread here asynchronously. So that means just launch it in a totally separate thread of execution. And until we use this value, we don't really care, if we get the result. It'll only block once we need to use this value, but otherwise it'll start doing work in a different thread for us. Okay. So here's the function getting launched in another thread here, this file loaded, which is just loading up some bytes. And it's doing so every 500 milliseconds. Okay, and we'll just pretend that's how fast the hard disk can read the data. This is just sort of a mocked up example. Okay, so if we run this, let me actually run it here. So I've got this example in our repo, so I'll just copy it over really quickly. If you want the async, just so you can see what it's actually doing. Let's get the raw code here. Open up a terminal. make it nice and big for folks. And launch it in Tmux, and let's call this async here. Okay. Whoops. Let me undo this and paste again. Okay. And this uses C++11 and the threading library here. You can see it linked in here. I'll go ahead and compile it, run the async, and then you can see from this code, let me go ahead and scroll down a little bit, just so you can see again what's going on is I have this loop that's running here. It says game is loading resources, and then it pauses, right? It just goes to sleep. But I've already launched this other thread asynchronously. So you're going to see, even though we're caught in this loop, we've just launched this thread that's just going to start doing work. And that's why you're getting these loading file messages here, okay? And otherwise, every 1 second, it's just going to say loading resources, loading resources. But we have other threads doing work for loading, this 3D object or something that's really big, okay, behind the scenes. Okay, so we're not being blocked. We have another thread that's working for us. That's the idea here. Okay, so we have another thread doing work for us. Threads are lightweight processes. We have multiple cores on our machine, so we should take advantage of them. Okay, that's what this example is showing. A little threading example with asynchronous I/O. Okay, right? All of our we pay a lot of money for our CPUs, so we should use their cores here. Okay. So again, the idea is one core here and another. This core is executing our main code here, maybe this first core here. And then this core is executing our asynchronous function here. Okay, and here's something of what the output looks like. Okay, if you want to see an example of this where you're streaming in data asynchronously, this is a nice one. Just sort of moving around the world in Minecraft. And you can see in the background this data just being streamed in. As we move around. So as needed, without any order, you'll see some of the ordering sort of randomly bring in the data. But that's the idea here, okay? Okay, so go ahead and give yourself another break if you need. We're gonna get to the final home stretch here, final slides coming up. And if you're joining back with us, a little puzzle for you. To do. Go ahead and pause the video and figure out how many resources do you see here. And if you're joining back with us, the answer for how many resources do you see? Well, a lot. There's textures, cubes, 3D models, grass, water texture, and so on. There's many, right? But why not this many? I see, I see just one cube here, one tree texture, right? It's repeated. So I don't see this, You could point to every little pixel that is a unique object here. Okay, and this gets to what our lab's going to be about, is actually building a resource manager. That's its second job, to manage resources. Okay, so loading a bunch of resources, one thing we could do is we could have a zip file, right? We could load lots of these different assets here. We bundled them up together. Why do we do this? Does anyone know, why are your files zipped up? Well, the answer is, if you've paused and taken a moment to think about it, one, zip's just an open format, so you can use it. There's no legalities, but the files are compressed, right? And if they're compressed, that means they take up less data, right? So that's why you download zip files on the internet. It's less bandwidth. If something's more compressed, it takes less time to download less data, okay? And then it's also easier just to pass around that one bundle of files, okay? But the other thing is, when you're loading here, you want to make sure only one resource is loaded. Why? Well, the why is because that resource can be shared amongst other objects, right? When I have one 3D cube, that's all I need in this game. I just need one 3D cube model that sort of defines its geometry. I don't need many unique variants of a cube, right? A cube is a cube is a cube. There's only one type that you have, okay? And that's always true, especially if the resource is static, meaning it doesn't change in the game, okay? Might be true if it's dynamic, but even this pig, right? These are all the same models here, okay? So every resource in your game, you should have a globally unique identifier. It's sort of called a GUID. And that means it's just a way to have a unique ID, sort of like a social security number that tracks the uniqueness of an object. Okay. So usually this means you have a hash, or a great way to get this good is just to have a hash of the resource file path, wherever you loaded it from, right? That's a great way to guarantee the uniqueness. Okay. So again, what data structure could you then use if you want to have or figure out if you have a unique resource that needs to be loaded? What's a good data resource where you can sort of hash things? If you thought about that for a little bit, a dictionary or a map in C++ or hash table is the answer. Okay. So again, the idea here is you have some sort of resource in your game, regardless of the internal format, if it's a PNG or JPEG or whatever, you need some sort of format that your resource manager understands these things. Okay, so it's going to load up the JPEG, load up a PNG, and you have a sort of image resource manager or texture resource manager. And each of those resources within that image manager gets a globally unique ID. Okay. So then another question, how long does a resource live once loaded? Because we've talked about memory allocation. Do I just load everything once at a time? Does it all go into the video RAM, main RAM? Where's it go? Well, the answer is, again, the resource manager will sort of take care of this. Okay, it's the resource manager's responsibility to start up and shut down a resource, or load and unload a resource. Okay, and we want to make sure there's only one copy of each resource in our game. Okay, we don't want to be wasteful. And again, we might have composite resources as well. So a 3D model, for instance, might have geometry, textures, maybe sounds associated with that 3D model, etc. Okay, so the resource manager will be sort of, or managers, you could have one for 3D assets, one for images, etc. It'll sort of manage all those things. Okay. So again, you could sort of manage or imagine some sort of data structure that handles all of these unique resources as they're loaded, okay? And you can load them asynchronously as you get closer to starting your game, okay? And again, depending on the resource that you need, you might again think about, is it something that needs to be loaded, synchronously or asynchronously? Okay, so full circle back to the asset management pipeline here. Okay, so it turns out that managing resources for a game has lots of trade-offs beyond performance. Okay. So we're going to focus on building a resource manager for our lab, which I'll talk about a little bit more in the live session. Okay. Just a little aside to wrap this up is, the resource manager can also be abstracted upon. So when you see this in like the Unreal Engine, you can see all the different asset classes that they have. Okay, particle systems, physical assets, materials, etc. They're all sort of laid out for you in the editor, which is kind of cool. And this is built directly on top of the resource manager that we're going to build. Okay. Naughty Dog has one, and they also build in different source control things with it, which is kind of cool. But the last thing I want to end with is just sort of a game engine design thing and clever workarounds for performance. Again, do you think it's efficient to load all this data at once? Well, we know now that all this data is maybe repeated frequently, which is kind of cool. So that's a really good thing. And then we know some tricks about asynchronously loading the data that's perhaps further away. Okay. And then we've seen stuff, if you've played some of these games, like this is Warcraft or some real-time strategy games, they have what's called the Fog of War here. And Fog of War was not only a interesting game mechanic, which hides areas that you haven't explored, but it was also actually a performance optimization where they could hide resources that hadn't been seen yet, so they didn't have to load them. So it was becoming hard. It was fast to load up part of the screen here, at game startup, but loading up the whole map is expensive. So throughout the duration of the game, different parts that you haven't explored or haven't explored in the wild will sort of darken, and they can hide the asset. So Fog of War was both a game mechanic and an optimization, which is kind of cool. Okay. Okay, so Fog of War uses a double-ended stack to achieve that by sort of unloading and reloading resources quickly. Okay, so that's just a little tip there. Okay, so let me sort of wrap things up there because my lecture is getting long enough, and there is an in-class activity for you. And then you'll be able to start your lab shortly on building a resource manager where we'll put together a lot of these ideas. There's a lot of ideas floating around in this lecture, so I just sort of scroll through it. Some of it's sort of refreshing you on systems types of stuff, but also just on a lot of these core systems. But we'll actually get to practice it in the lab and put everything together. All right, so we'll talk to you very, very shortly, and see you soon.